Hello and welcome to Chapter 1, Section 3. This is representing and describing transformations. A transformation is a function that changes the position, shape, and or the size of a figure. So the figure that you start with is called the pre-image, and then the image is what you end up with after you've translated it, which means you've moved it around, or you reflected it over a line, or you rotated it. Whatever the output shape is called the actual image. And we talk about them using prime notation. So the pre-image might have point A, but when you move it, that becomes A prime. And that's the actual image, and that's how we read it. This is a little 1 up here. We read it A prime. So if you look at example A on the bottom of page 31, our pre-image points are A, B, and C, and they've drawn you a nice little picture of what A, B, and C look like. Nice little triangle that's a right triangle centered right at 0, 0. And the rule is x minus 4 and y minus 3. So we're going to start with A, and we're going to say x minus 4 is negative 4, and y minus 3 is 1. And with B, x minus 4 is negative 1, and y minus 3 is negative 3. And with C, we have negative 4 and negative 3. When we go to graph this, we've started with A, B, C here, and now A prime is in negative 4, 1 here, A prime, and B prime is in negative 1, negative 3, and C prime is in negative 4, negative 3. So now our shape is here. And so this is a translation. It hasn't rotated or flipped at all. It's just down, it's just slid down diagonally. So, they do want this part in words. The transformation is a translation 4 units left, and you can see that here, 4 units left and 3 units down. And in comparison, it's the same size and it's the same shape. So we didn't hurt it at all. We didn't change the shape at all. So pause here, do B and C and the 2 reflection questions, and come back when you're done. With B, because we made x negative, we've actually flipped this the other way, and we flipped it over the y-axis. So R, S, and T prime are exact opposites across that y-axis, almost like a mirror. So it's the reflection across the y-axis, and it's the same size and shape, but it's flipped. With C, here are our shapes. Whoops. Here are our points, and we've multiplied x by 2. So what that does are, because x tells us left and right, it's actually stretched out our new triangle. So it's got a horizontal stretch by a factor of 2. They're both right triangles, but it's a different size and a different shape. Okay? And in going back and looking at the past ones, A and B were both the same size and the same shape, but it changed in C. And then for number 2, it asks for you to map the image back to the pre-image. So it's the reverse of the rule. How do I get back to where I started? So that's x plus 4, x plus 3, negative xy, and 1/2 xy. Next, we're going to talk about rigid motions using the coordinate rotation. So rigid motion changes the position of something, not its size or its shape. We're keeping the shape rigid, the same as it is. We're just moving it around or flipping it over. So the properties of rigid motion mean it preserves the distance between all the points. It preserves the angle measurement. It preserves the betweenness, which is a word I hate. It preserves collinearity, so anything that was in a row before is still in a row. It preserves parallelism, so if you're graphing a shape like a square or a rectangle, whatever lines used to be parallel are still going to be parallel, even if the shape is tilted, the lines are still parallelism still stays. And it's always easier to look at something that's moved. This has been rotated around the origin 90 degrees counterclockwise. So it has preserved the distance from the origin and from the axis here. It's preserved all of the angle measurements. It's preserved whatever's between it. Anything that was on the line still are on the line, and any lines that not in a triangle, they're not going to be parallel, but you understand what I'm saying. Now for the next example, we really want to look at the question. The question on page 33 asks us to use the coordinate notation to write the rule that maps each preimage to its image, then identify the transformation, and confirms that it preserves length and angle measures. Now look at all the work that it takes to do that. It goes all the way to the bottom of the page. Let's take it apart. We're going from ABC to ABC prime. We are actually rotating this 90 degrees counterclockwise around the origin. So we want to figure out what's the pattern in the coordinates. Well, we have to actually look at the x's and y's. And I go from 1 to -2 and 2 to 1, 4 to -2, 2 to 4. It looks like I'm switching x's and y's. And I've got negative signs in there, so we've got to figure that out. And it turns out that we get our new x from -y. So we look at y, make it negative, that's our new x. And our new y is just x. So here, we look at y, we make it negative, and we steal x. We look at y, we make it negative, we steal x. So this is our pattern. What it does, it's a rotation counterclockwise 90 degrees around the origin. So I need rotation, I need how much of a rotation, I need what direction, and I need what it goes around. And then the rule is pretty straightforward. I went from x and y to my x prime is really -y, and my y prime is really x, -y and x. Then it asks us to find the length of each side to make sure that it preserves its length. So I need A, B points and A prime, B prime points, and I need to throw it into the distance formula. And in your book, you can see I need my A, B length and my A prime, B prime length. Now, because they are right in line, I can just count 1, 2, 3, 1, 2, 3. They're 3 units each. So AB and A prime, B prime are both 3. The other ones, because they're not in a straight line, they, on a coordinate plane, we need to throw them into the distance formula, and in your book you can see that they've done that, and you can follow the math, and you can see that BC and B prime C prime are both root 17, and AC and A prime C prime are both root 20. So we've determined that the lines are the same size. The next thing we have to prove is that the angles are the same. And that we do with a protractor. So you pull out your protractor and you measure them. So, and what we found is that the side length is preserved and the angle measurement is preserved. It's because we've gone through those steps. Now we go back to the question, because it's a big question. It says, use coordinate notation to write the rule. Well, our rule is we went from x, y to, how'd we get these two? We went to y, we made it negative for our x, and we just stole our x for the y. The next thing we said is identify the transformation. It rotates 90 degrees counterclockwise around the origin. And then it's confirm that it preserves length and angle measurement. And so we used the distance formula for length and protractor for angle measurement. So we've answered all the questions. These are big questions that they're asking. So let's do another one. So now try the next one for yourself and do reflection numbers 3 and 4. Pause here and come back when you're done. So B, the x coordinate equals the other one, but the y coordinate is the opposite of, or the negative of, the y coordinate. It is a reflection across the x-axis, and our rule is xy goes to x negative y. So if you look, all the x's are the same, but all the y's are just negative whatever they used to be. So this is our rule. And when we put it in, and when we add all of the numbers into the distance formula and we measure all the angles, we get all of our numbers here. So we see that they're the same length, and we see that both sets of all the 3 sets of angles are equal to each other. Reflection number 3, you're going to open your compass to one line length to measure for the other line length. And number 4, the first A is rigid, B is rigid, C is not rigid. So take a minute to try your turn numbers 5 and 6 to make sure that you can do this walking through it all your own. Pause here and come back when you're done. So with number 5, the pattern is that each coordinate maps to its opposite, or its negative. The transformation is a 180-degree rotation around the origin. Doesn't matter what direction it goes, because 180 is exactly halfway. The rule is xy leads to negative x, negative y, because those are the opposites. And then we check to make sure the lengths are the same, and we check to make sure that the angles are the same, and we note that the side length and the measure of the angle is preserved. For number 6, we've done the same thing. The pattern is with x we added 1, and with y we subtracted 2 each time. So this transformation was actually a translation. It moved it slid it down, and the rule is x plus 1, y minus 2, and we measured all of our lines and our angles, and those were preserved. Next, we're describing non-rigid motions using the coordinate plane notation. So rigid means that the shape stayed the shape, we just moved it around, but it didn't mess with the shape at all. This one is messing with the shape. This is when transformations stretch or compress figures. So here, if we start with JKL and we end up with J prime K prime L prime, our pattern, well, X is always X, but Y, the first one is Y plus 2, and the second one is Y minus 2, and the next one is Y times 3, but they end up, actually, if you look at them, they're all Y times 3. If adding and subtracting doesn't work for you, try multiplication, because this one is Y times 3. When I start comparing the line lengths, JK is root 40, but J prime K prime is root 72. So already I know that it's not rigid because they're not matching. I don't have to do any more. I know that it's not rigid. So we're going to stop here, and I'm going to ask you to try B and reflection number 7. So B is twice and half and 2x and 1/2 y, or 0.5 y. And when we start measuring line lengths, we see that M and N are not the same, so this is not a rigid shape. And then reflection number 7, if all the angles were preserved, it might be rigid, but we'd still have to check the line lengths to make sure.